I'm Ray McGarry, and I'd like to talk to you about reverse time migration, or RTM, using the Acceleware AXRTM toolkit. Let's start with a very brief introduction to RTM. So RTM is very much a state-of-the-art technique for imaging subsurface geological structures from recorded seismic data. Unlike most other seismic imaging techniques, RTM considers natural propagation of seismic energy without numerous simplifying approximations. And this enables imaging of very complex structures, or even beneath salt formations. And here we see an AXRTM image of complex foothills geology. Now, the strength of RTM stems from the fact that it uses the full two-way wave equation to model propagation of seismic energy through the earth. And this ultimately means that there's no dip limitation on the features which can be imaged. And it also enables RTM to use both turning and prismatic rays for imaging, as shown here. Now, the superior imaging capabilities of RTM come at a cost. Compared to other imaging methods, RTM can be orders of magnitude more computationally intensive. And the scale of the problem becomes clear if we appreciate that the first step of RTM is to discretize the image volume onto a mesh. And typically there may be hundreds or even thousands of mesh points in each dimension. And the wave propagation at the heart of RTM requires wave field update calculations at each of these mesh points. The key parameter in determining how many mesh points there are is the migration frequency. And here we can see that there's a non-linear relationship between frequency and number of mesh points. So for example, doubling the migration frequency can lead to an 8-fold increase in the number of mesh points. So a lot of calculations need to be performed to do a single wave propagation update. But those calculations need to be performed thousands of times as we march our solution forward and indeed backward in time. So we can see that RTM is very computationally intensive. And of course, this has led to a very slow adoption of RTM for production imaging. And even now that it's becoming a standard imaging technique, the quality of the images produced can still be limited by the need to migrate at reduced frequencies, just to keep the computational requirements to manageable levels. So RTM is very computationally intensive, but it's also very memory intensive. And there are what I call traditional memory requirements associated with wave propagation and imaging. So for each propagating wave field, we may need to store 2 time snapshots. Of course, we'll also need to store the image and a velocity field, and there may even be others, for example, anisotropy parameters. But in addition to these traditional memory requirements, we also have very considerable extra memory requirements, due solely to the reverse time nature of RTM. As we can see here, RTM works by marching a source wave forward in time from the source location, and a receiver wave backward in time from the recorded seismic data. Now, to produce the image, these 2 wave fields must be correlated at the same instant in time. So in our very simple example here, the first calculated source wave field must be correlated with the last calculated receiver wave field, and so on. And what that means is that we can't simply propagate both waves together and correlate as we go. We need to find some way of accessing the source wave in reverse time order for correlation with the receiver wave, which is being propagated in reverse time order. Now, the simplest and traditional approach is to perform the source wave propagation and save the full wave field at every mesh point in every time step. So this data is then available for correlation while reverse propagating the receiver wave. Now, this involves terabytes of data, which obviously can't be stored locally, so it tends to lead to very serious I/O bottlenecks. And later we'll look at some alternative strategies for dealing with this issue. So now we've seen the scale of the problem, let's look at the Acceleware solution, AXRTM. And what is AXRTM? Well, it's a full-featured production-ready RTM toolkit. Now by toolkit I mean it's a collection of library routines which perform, on the one hand, the entire functionality of a full-featured RTM application, and on the other, all of the functionality required to squeeze maximum performance out of whichever hardware platform it's being implemented on. Now, being designed as a toolkit, AXRTM is highly flexible. So it's written in a completely modular fashion, and the library routines are easily accessed via a well-defined API written in standard C. Now, it's very important to realize that AXRTM can be run as a full standalone RTM application. But at the same time, we recognize that many users will want to take advantage of many of the features of AXRTM, for example, optimize wave propagation, but also incorporate their own expertise. So for instance, they may want to use a proprietary imaging condition. And the toolkit nature of AXRTM makes this very easy to do. A key design principle of AXRTM, and indeed all Acceleware software, is that hardware optimizations should be abstracted as far as possible from the top level application. And AXRTM is of course highly optimized, and that optimization is addressed on two fronts. So firstly, there are hardware optimizations, and AXRTM is currently optimized for maximum parallel efficiency on the latest CPU and GPU hardware. On other platforms will be supported as they are introduced. The second strand of optimization makes use of the very latest algorithmic developments, and I'll mention just a couple of these later. So let's look in a little bit more detail at hardware optimization. Well, of course, a typical RTM job has to be split across multiple compute resources. And the key to doing this efficiently is to minimize communication and to reuse data as much as possible. Now, parallelization across multiple shots is a relatively simple task. The much harder task is to distribute a single shot migration across compute resources. Now, AXRTM handles all of that, so it'll take care of partitioning a single shot migration both within a single node and across multiple nodes if necessary. And here we see an example of a migration being split across two nodes, each with 2 GPUs. Now, AXRTM makes no assumptions about hardware configuration. It'll simply use whatever hardware is available. So it'll quite happily run on CPU only hardware or a heterogeneous cluster of both CPU and GPU hardware. And I'll just stress again that hardware optimizations are abstracted as far as possible from the top level RTM application. And of course this greatly reduces both costs and effort associated with maintenance. Well, now I'd just like to mention a couple of the algorithmic developments which contribute to the excellent performance of AXRTM. And the first is finite difference optimization. AXRTM uses finite difference techniques to perform the wave propagation calculations at the heart of RTM. And these have been optimized in terms of both the finite difference operator and the finite difference grid. Now together these optimizations lead to significantly improved performance and to a much smaller memory requirement, as we can see in the graph here of total memory requirement. The second algorithmic development I'd like to mention concerns reverse time accessing of the source wave field. There are various possible approaches to this, and the traditional approach, which I mentioned earlier, involves simply saving the entire source wave field in the forward propagation phase. And this requires terabytes of storage and leads to very serious I/O bottlenecks. A more clever approach involves a technique known as checkpointing, where the source wave field is saved just a subset of the total number of time steps during the forward propagation. The Acceleware preferred approach uses a high fidelity reconstruction of the source wave field using a minimum amount of data stored during the forward propagation phase. And we can see in the graph here how this approach can lead to very significant reduction in the total storage requirements, even relative to checkpointing. Now, of course, in practice, the best approach may well depend on the specific situation, and Acceleware can advise on the best approach on a case-by-case basis. So now let's look at some of the specific feature support in AXRTM. Well, obviously it handles isotropic migration, but it also fully supports migration in anisotropic geologies. So both VTI and TTI anisotropy are supported. And here we see the need to use fully anisotropic migration in areas where the geology is significantly anisotropic. So both images show the results of migrating the same model with isotropic RTM on the left and anisotropic RTM on the right. The model has significant anisotropy caused by tilted sediments. So on the left we can see that the salt flanks have either not imaged at all or they have been imaged at the wrong location. And by contrast on the right we can see that TTI RTM gives good imaging and location of the salt flanks and the sediments. Now, it's well known that anisotropic RTM can suffer from numerical instabilities. And there are two types of such instability. The first, which affects only TTI, arises at sharp contrasts in dip or azimuth angles. And the second type of instability affects both VTI and TTI and places fundamental restrictions on the relative values of the Thomson parameters. And these Thomson parameters characterize the strength and the nature of the anisotropy. Now, AXRTM implements measures to avoid both types of instability. And it remains stable for arbitrary variations in dip and azimuth angles and arbitrary variations in Thomson parameters. So here at the bottom we see quite a complex synthetic model with significant TTI anisotropy. I notice on the right that there are several areas with very sharp contrasts in dip angle. Now, without measures like those implemented in AXRTM to avoid instabilities, these sharp contrasts would make it impossible to produce an RTM image of this model at all. But here we see that AXRTM has been able to produce a very high quality image. And in particular, we have very clear imaging of the areas with the sharp dip contrasts. No instabilities have arisen at all. So now let's briefly look at some of the other specific features supported in AXRTM. Well, it supports both 2D and 3D migration. Absorbing boundary conditions to terminate the model are very important for avoiding unwanted artifacts in images. And AXRTM includes a range of different absorbing boundary conditions, including state-of-the-art CPML boundaries, which Acceleware has pioneered. And various high-quality imaging conditions are supported, including simple cross-correlation and a directional decomposition imaging condition for reducing self-correlation noise. And of course, client's own imaging conditions can easily be incorporated. As a byproduct of RTM, an illumination map can be generated, and such a map may have a variety of uses, for example in normalizing images, or even in survey design. And finally, AXRTM is fully MPI capable. Of course, this helps with domain decomposition and data synchronization. So, I'd just like to summarize some of the key customer benefits from using AXRTM. And we'll divide these into three main groupings. So first, there are geophysical benefits. AXRTM enables high-quality RTM and forward modeling in isotropic VTI and TTI media. The finite difference techniques used for wave propagation are very highly optimized both for performance and for image quality. And of course, AXRTM includes many other state-of-the-art developments and features. So secondly, there are software and design benefits. As we've seen, the computational kernels of AXRTM are highly optimized for the latest CPU and GPU platforms. The modular nature of the code and the well-defined API enable simple, flexible integration with existing software. And thirdly, there are maintenance and time-to-market benefits. So, abstraction of the hardware optimizations from the RTM application has very clear benefits in terms of maintenance. The use of the AXRTM toolkit, of course, enables very easy access to speed. Now, Acceleware is committed to supporting future high-performance computing platforms as they become available. And one effect of that is to effectively future-proof our customers' RTM applications. So, I'd just like to finish off by showing a real field data example. So this is an AXRTM image from a 3D OBC survey from the Gulf of Mexico. And the data was migrated using a maximum frequency of 33 Hz. So I think we can very clearly see that we have good delineation of the salt body and also of the sediments abutting the salt. Well, thank you for watching this Acceleware webinar. If you have any queries, please don't hesitate to contact us at the email address shown here, or visit our website for more background. Thank you.